So we can slowly start our second lecture in this course that I call 4 lectures in solid state physics, and the focus is on electrons in periodic solids. As we just discussed with you now before we started, this is not so simple. It's not a trivial topic, indeed. For that topic, usually you need to know many other subjects. Like, preferably you should know statistical physics, quantum physics, and that is actually application. Because electrons, they are particles, and they are also waves. So this is really a tricky thing. But to understand properties of electrons, and then understand optoelectronic properties, basically, that's our target, or your target in your studies. We should actually, I think, try to simplify the situation and take it from its whole complexity to some more simple interpretations and examples. And this is what I tried to do in the first lecture. Let us go through very, very fast. This was our plan for the first lecture, and we reached up to here. So we went through these topics, and the major part of, I think, message that I have had is that electrons are waves, and they really behave similarly like all other type of waves in crystals, in periodic structures. And for explaining that, for introducing that, we looked into a phenomenological situation when, for instance, you can think about that as an electron wave coming to the grid of planes. Electron wave is a k vector, and then this vector is diffracted to k prime. It can be any wave. It can be X-ray, electron, elastic wave. The only difference in the waves, actually, is the magnitude of this. Some waves have this big, what's called wavelengths, and some waves have this small wavelengths. Then these having big wavelengths, they will have very small k number, because k number and lambda, they are proportional like this. Yeah. So k is measured in say, reciprocal units of length. So then what we discovered, or what we repeated, what was the really the important part, or a conclusion, that we discovered that if you have a wave, and this wave is diffracted by the lattice, then the only way to it to get diffracted by this specific family of planes is that the wave, the magnitude of this, should be exactly half of the reciprocal space vector for this particular family of planes. And these points are very important then. So, and this is so-called Bragg plane, and then if you build all these Bragg planes for all reciprocal points like this, so we will get a space in reciprocal. We will get an area or volume in reciprocal space that is actually called Brillouin zone. And the Brillouin zone tells us that if the k vector is, the magnitude of k vector is smaller than the size of Brillouin zone, then this vector will never interact with the crystal. It just cannot. It's like me not speaking Korean. I may be actually quite intelligent, but if I don't speak Korean, there are some places I just don't need to go here because I will not be able to interact. My Korean is not even that small, it's this small. And exactly for this vector as well. If the magnitude is too small, it will not interact. The magnitude should be exactly or very close to the position of the edges of the Brillouin zone. Then this wave will interact with the crystal. And this is a very, very big thing, because it actually immediately brings us to electrons. Because we know that many materials have very high electron conductivity, electronic conductivity. And this is very strange, because what conductivity does mean? Conductivity means we have a lattice. Okay, this is a lattice. And then somewhere here we have many electrons. So these are positive charges, lattice. And these points are electrons. And these points are actually negatively charged, correct? Electrons are negatively charged. So if you think about this system like only particle system, there is no way, for instance, for this electron, this is positive charge, this is negative. If this electron wants to pass by this place, it has to interact. This is positive, this is negative. They will just get close to each other. And then this way will get changed like this, correct? But it is not happening. Really, in metals, the resistance or resistivity is very low. So if you calculate it back, there are no collisions of electrons in metals with ions at all. So electron can travel, if you make a measurement for electrical resistivity, you can measure a value that will bring you to the idea that diffusion, let's call it lambda, the mean diffusion path, the mean distance the electron can go without collisions is some 1 millimeter. It's very huge, because this distance between atoms is some 5 angstrom or something like this. So 5 angstrom is much, much smaller than 1 meter. But somehow electrons can travel this big distance. And the reason for that is exactly this. As long as electron K number, electron wave K number, has a low magnitude, then the waves, they simply don't interact with the crystal. So for you who just came, so we are repeating a little bit from last time. And what we are repeating is that just because of diffraction conditions, because Bragg diffraction, Lauer condition, all waves, they have K numbers smaller than the magnitude of the Brillouin zone, will never interact with the crystal. This is the reason for high electrical conductivity. Because if it would not be like that, no materials are going to conduct. Because they will just like this, like collide all the time. And actually the first model for conductivity in metals was exactly like that. Because nobody knew that electrons are waves. Or at least there was no this concept. So electrons being considered as particles, and they are being considered as classical particles, and it's been strange thing that the calculated, the measured mean diffusion path is 1 millimeter, but the distance between atoms is 5 angstrom. It was a huge mystery. Why? And then it came the idea that electrons are waves. And now we can deal with that and explain it. But the core explanation is really very simple, or at least it can be interpreted very simply. As long as this thing is small, just doesn't diffract. It's like if I go, if I know where to go, so to say, if there are these roads, you see, it's very periodic. If I go here, I reach very far, correct? I reach to the window there. But if I try to go here, it's no way, it's an obstacle. And electrons sort of clever. They see that they can behave as waves. And so to say, sneak around these lattice. This is a fantastic property of electrons that is not always really understood by students. Because sometimes you think it's so simple, it cannot be the truth, but it is the truth. Right, so after this introduction last time, so we went to more specific calculations that everything I said by now just been hand arguments, correct? But we can actually write this equation, which is a bit scary equation. It's a Schrödinger equation, but it's good. It's not a big problem. It's an equation that connects two types of energy contribution, or two types of energies that affect wave function, electrons. It can be potential energy and it can be kinetic energy. And then the idea of this equation is to see how kinetic energy and potential energy influence the wave function and calculate what I allowed energy state. This is what this equation is about. It's like, again, if you give me a chance to make some comparison, it's like you have several contributions to your behavior. Let's say there is some rational contribution and maybe irrational, and you always have to take into account. So I don't say that kinetic energy is irrational, but somehow it's more kind of basically it depends on temperature. And this is the potential energy, just telling us what are the potentials. And the first approximation to do is to just neglect this potential energy and think that the whole crystal is the whole crystal, the whole sample is just a potential well like this, which is actually quite reasonable, because if I have a sample, I can think that these walls, basically electrons cannot go outside. They have some potential to overcome, to go outside. And we think that potential is so big that all electrons are here, basically. So this is our sample. It's not complicated in the end. It's actually quite rational. People who've been creating this theory, of course they've been genius, but not that, genius from another planet. I think they had arguments like that. Okay, this is our sample. We think, how can we simplify this equation? Just put this to 0, and we can see our solution only in here. That's already a simplification. And then this equation, it can be solved because it's just the second derivative. Maybe you don't know this. Not everybody knows what is this, but it's just second derivative. It's if you have one-dimensional situation, say I have my sample only in one dimension, in the direction x, then this one is just that. So that's just this. We derivate 2 times. And then we also discussed it. I think someone, I don't remember it now. We discussed if we have second derivative here, and the function, and then we have no derivative here, and we want to get So forget about this. This is 0. So we have to make sure that this part is equal to that part. And there are not so many functions that when we derivate a function, say there is a function, and when there is just a function, how to make it equal. There are very few, actually. Basically 2. Of course, there is an exponential function. We put it in here, we derivate, but it doesn't change. It's a very nice function. Or it can be a sine, because 2 times it will be back to sine. Is minus here, which is very good because we have to remove this minus. Yeah. Correct? So when I derivate sine first time, it will be cosine, and cosine derivated second time bring me sine back. Is a minus. So two possibilities. If we immediately take this possibility, because that's most general, so we immediately see that our function should be of the shape of the exponent. And what should be here in this exponent? Obviously, it's a wave. So what we should have here, we should have a coordinate, in this case x, but more generally just distance in all 3 dimensions, and actually k vector. That's it. And then we have this sign here, so that makes the wave wave. Yeah. So that's our solution. But then I would say even this is not that complicated math. It's still the math. And some of you maybe don't do calculations every day of this type. And you can think, what is it? Maybe it's too complicated, maybe unnecessary. Okay, let's make a step aside. We don't do this calculation. What are we doing really? Yeah, once again, we want to find energies of electrons, correct? Because the energies of electrons in the end of the day determine properties. The high energy, these properties, low energy, these properties. It's not really a joke. It's necessary to know energy of electrons. So we want to calculate this. And we said there are many electrons here. So the thing is, maybe I can ask a question. Do you think, of course, as we all, electrons probably, I don't know, could we call them lazy? But of course, as everything in nature, if they would have an option, they will all get as low energy as possible, correct? It's like us. If I don't need to come to this class, I would stay in my hotel and probably watch some YouTube. Okay, maybe like you. But what about electrons? So we have, in this material, how many electrons we have? Okay, not in this, not in one dimension. Say we have 3-dimensional material. One mole or whatever. You know how many electrons we have? For instance, in sodium. How many electrons we have in one mole of sodium? 6. Okay. You know this. How many atoms we have in one mole? It's Avogadro number, correct? You may not remember that. Actually, I remember, but I can pretend I don't remember. But is it a big number or small number? Huge. Let's say maybe we come to more. Who knows about this sodium? It's a really unnecessary material for us. But if you deal with semiconducting films, for instance, silicon is a nice material for us. Even it's not so good for optelectronics. In 1 centimeter cube of silicon, there are 10 to 22 approximately atoms. Approximately. And silicon, it has 4 electrons, correct? On the outer shell. So potentially it can donate, all these electrons to make it free. It's not really happening because their covalent bond is so great, so stable. But potential, but we should at least have at least this much electrons. So quite a lot in 1 cube of 1 centimeter cube of silicon. If you have so many electrons, do you think it is possible for all electrons to get zero energy? If you have so many customers and we have a lot to sell, will we sell all our products to low price? Never. Never. We will try to make some profit immediately. When we have this many customers, we will immediately say, no, this low price. We pay us more. And it's something that happening here. Some lucky electrons can get low energy, but not everyone. There should be some distribution. And this is what we can calculate mathematically. But it's actually quite obvious, correct? If you have this equation and we want to calculate energy, I mean, the best case for anyone is to be here. No problem, no work, good. Maybe not that good. It depends on attitude, but it's human. But electrons will definitely get the lowest energy. But they cannot, everyone, because there are so many. And then my question is, or let's say, then there is the idea of orbitals. Because when we calculate this equation, then what we really get is we get, I just copy what we have there, this well. So we get that somewhere here on the first orbital, we have 2 electrons. And on the second orbital, we have again 2 electrons. But basically what this equation will give us, it will give us, this is energy scale. It will give us positions for these electrons, for this orbital. But then, let me ask you a question. Why do I do it this way? Why can't I place 4 electrons on this orbital? Or maybe 5? Why it is only 2? It has nothing to do with gender, unfortunately. Otherwise I would make this. But sorry about this joke. Why do I put 2 electrons on one orbital? Because they are so-called fermions. Electrons cannot get the same energy. We already discussed that probably not everyone can get an energy equal to 0. But more than that, only 2 electrons can get exactly the same energy. Because that's a property of electrons that was discovered. We cannot place 5 or I don't know, 10 or even 3 electrons for one energy. So only 2. So why? Because they have to be distinguishable. Electrons, they have energy and they have plus or minus spin. Then we can use that. So that is necessary, that electrons can be distinguished. And then this equation will calculate all these orbitals, and we will know exactly what are the energies of electrons. And then it will go up to some value, some highest value of energy. And this highest value of energy is called Fermi energy. And then again, why it is highest? Very simple, because we have huge, but still limited number of electrons. If this number would be infinity, there would be never reason to get the highest energy. But if you have 10 to 22, we put first 2, then 2, then 2, then 2, and then we just out of electrons. It's just not available. So here, when we calculate, it's interesting really, when we calculate these positions by this equation, we think that electrons are waves. But when we place them on the energy orbitals, we think they are particles. It's always very interesting consideration here. And then because they are particles, they have a limited number. There is a limited number. And then up to this level, orbital, we have electrons filling orbitals. But after that, there are no electrons. That's natural. There is really no, let's say, there are so many really curious problems in science, matter or gravitational waves. Nobody can see that, except, I don't know, complicated equipment. Or here is actually quite simple. We have number of particles, we have number of electrons. We know that all electrons cannot get the same energy. They have to get different energy, and then we just place these particles in here. So then we have the highest energy here, and then also what is probably good to remember that the solution of this equation is that. So the energy is equal to its square of k. So that is exactly the solution of this equation. When you put, you will have, when you differentiate, obviously when you have this function here, and you differentiate it 2 times, this is nothing, but k will come up to here, k squared. So that's why. Obviously, it's actually shown here. So if I plug this function in here, I will get this solution. And then we can draw that. We can draw this this dependence. So I'm sorry I'm spending this time. We actually went through that last time, but I think it's worth to do it. We don't need to rush, actually, correct? So it's better we understand a part than we understand nothing. That's my usually idea. So then if this is a solution, and this is k, and this is energy, and the dispersion relation is like that. It's k squared, proportional to k squared. Correct? Oh, it's not really good. It's better like that. And then we can come back to, not come back, but to think, what is this? This is just wave vector, correct? So each of our wave, so we can also come back to this cartoon. So here we say that energy can be any. Of course, this we also talked about. Of course, this is not really a continuous line. There are many points here, correct? But these points are very close to each other. These are really points of K. Because the crystal is limited. The crystal is limited. So we cannot have an electron wave longer than this. And that is going to give us the smallest K number, correct? If this is length of the sample, then the smallest K is actually pi over L, correct? This is just a coefficient. You can say if this is lambda, then K is 1 over lambda, 1 over L. And then we have a coefficient here, pi. But, okay, these are discrete numbers, but they go all the time, even they are very close to each other. It actually depends how big is L. If L is 1 centimeter, then there are plenty of these points. But if L is 10 nanometers, then the points are quite discrete, like in low-dimensional materials. But what actually I wanted to say is, all these calculations we done with thinking that electrons are not colliding with anything, that potential energy is 0, only kinetic energy is involved. And that is true. Again, we come to this picture. That is true for low K. No interaction. So if K is low, just wave go through. not interact. But if wave getting big, so what I want to say is this dispersion relation is actually very good here. When k is small, it's perfect. But when k comes to the edge of Brillouin zone, this approximation is no longer good. And edges of the Brillouin zone, where they are. If this is the longest wave, what is the shortest wave? The shortest wave is actually, we can think about is the interatomic distance, correct? It cannot be shorter. So then the shortest one is just A, correct? The lattice parameter. And the reciprocal, so lambda is equal to A. And then the reciprocal number, K, is going to be 1 over A. So somewhere here, and then if we include pi as a coefficient, we need it. Yeah, but it's just a constant, doesn't matter. So it means that somewhere here, at pi over A, and somewhere here, at minus pi over A, for one-dimensional crystal, in these places of K, so this solution is not good because K is so big. It starts to interact with the edges of the Brillouin zone, or actually with the crystal, but not with the Brillouin zone. Brillouin zone is just an imaginary thing. The waves start to interact with the crystal when this magnitude matches the Brillouin zone. So it means somewhere here we have some problems. And but it's actually, these are not problems. This nature. It's like you just learn it and use it. This is what actually semiconductor physics is about. Because here, basically this is semiconductor behavior. When electrons are diffracted by the crystal. This is a typical sort of free electron metal behavior. And what is happening in these places that there is a deviation. There is a deviation from this simple solution. So the solution then gets like this. And then we have a band gap in exactly this position, these values of K. So here we have this. This is exactly why we have the band gap. So the only reason for band gaps and just not continuous energy structure is by the crystal. There is no other reason. Okay, so this was a repetition from last time. Yeah, and then we can calculate three-dimensional things. So you see, now we've been talking about one dimension. So the biggest was this, the smallest was that. If you have 3 dimensions, then of course we have this multiplied together. We have a cube. So this was just the smallest distance in the reciprocal space. Sorry, smallest is this one. And if you multiply it 3 times, we have a volume in the reciprocal space that is dedicated to one orbital, one state. And then we can calculate it, and now we can connect. But basically it's the same thing like here, like we talked qualitatively. This is the number of electrons we have. This is exactly 10 to 22. Then this is the total volume in the K space that is available. So we have it here. And this is the volume in the K space for one orbital. It cannot be smaller. This we know. So if you make a ratio between everything we have to the one that is dedicated just to 1, and then we multiply by 2 because there could be 2 electrons here, exactly like I drew it here. So every orbital, every state can accommodate 2 electrons. So here we can have 2 electrons inside. This is these 2. These are just these 2 volumes. And this is equal to n. So when we have this equation here, so then we can elaborate on that, and then we can find a function that connects energy and how dense, how often this, what is the distance here? Is it linear? Is it quadratic? Is it whatever? So we want to know this dependence, how this is distributed. Then we can have a equation and we can do the formalism. Then this can be extracted from here. And then what we said, in this case, for 3-dimensional solids, we have this solution. So this is the square root of energy. This is how these are distributed. So we can also draw like this. So here is the first one, second one, like I put it here. Third one, and then here is n over 2. Why it is n over 2? Because we have 2 electrons on each orbit. So all these orbitals are taken. Yeah, and this is at 0 Kelvin. So actually at 0 Kelvin, basically we know everything now. What is the status of our electrons? So we know that they are filled, they have energy up to here, up to Fermi energy. Maybe I better draw this like that, and I have like this here. This is Fermi energy, exactly like this in 1 dimension. This is more sophisticated and more correct. So we have this distribution function, and we have 2 electrons on each of the orbital. So all these orbitals are filled everywhere. And here we still have orbitals, but all these orbitals are empty, because simply as we talked here, we don't have more electrons. We put all electrons already on the orbitals. Yeah, it took some time to talk about this, but let me continue. We have a couple of minutes to continue. To go really over to the topic of today. So this math is just how to get this equation, how to get this form of equation. You can definitely do it yourself. We don't do it much here. But what I wanted to go to is to that. This is where we should start today, actually. But I think it's good that we devoted time for repetition. At temperature equal to 0, you know that the electron system is like this. What is happening when temperature is increasing? Then, what do you think is happening? What we know is when we add energy, of course, lucky guys, they go to high energy. But what is the distribution function that governs this? For fermions, it's Fermi-Dirac distribution. And the form of that is actually quite complicated. It's even difficult to remember, I know. But it's not so critical that you may not exactly remember this form, because you always can get it from a textbook. What is, I think, more important is to analyze what is happening with this system when temperature is supplied, when temperature is increased. And this I have on that plot. This I think we have to stay for a while. So, do you know what is typical, do you recall it, what is typical KBT value at room temperature? What is the average kinetic energy of an electron at room temperature? This is that. Do you recall how big is that? Anybody? Yeah. 0.025, I would say. It's even low. It's actually very low. And this energy here, thermal energy, is actually much bigger. For instance, for this material, for sodium, why sodium? Because it's so typical metal, so good. But actually, it's not that much different for other materials. So basically, the rule of thumb is that this value, this one, is much bigger than that value that we can reach by temperature. What is then happening with our electrons? So this I try to visualize here. For instance, this electron, this here electron, it cannot be excited by this energy. Because if I put this energy on that electron, he cannot really get excited to this orbital here, because this orbital is already taken. For instance, this electron cannot go here, because this orbital is already taken by two other guys. Oh, it's like these desks. You see, you have two desks close to each other. If somebody wants to jump in, no way. This place is taken. But this guy, of course, he can jump to high energy here. And this is what leads to a situation that some of the electrons from here, as it is visualized here, you know, initially it was just sharp function, no distribution. But now some of the electrons here, they increase the energy up to there, but there are very few still. But it is exactly these electrons that we going to consider actually in the rest of the course, and that are really meaningful in semiconductor physics. It's not really all this. It's actually only a portion of electrons. And these are electrons that, for instance, contribute to thermal properties. Because electrons at with low energies, they just cannot accept energy, cannot accept kinetic energy, because they are blocked by other particles there. But only a very small portion of electrons can take this energy and get excited. So that is fine. So let us believe that we made a repetition and we take a rest now, and then immediately go to this, because I also know that it will be kind of also slight repetition of what we said, but this is going to be the last basic point of not related to semiconductors. After that we go to semiconductors. But I want really once again to discuss what is the origin of the bands. We already said that the origin of this behavior, that there is a break in the dispersion curve, is the interaction with the Brillouin zone, with the crystal. But let us repeat it in the second hour again, that you can answer me on these questions. Usually I don't know, this is really our topic, electrons in periodic solids, and these are kind of silly questions, stupid questions, that you can ask. And I wanted to ask you these questions. Say the first one I'm going to answer myself. This one I want you to discuss. So I really want to claim that the sample, the solid, is a wave box. Because the result of, at least as it holds to electrons, every property that is coming out of the material is the result of interaction of electrons with the lattice. There is really no more influence. Really no more. If you think about zero temperature. And then when we heat the material, then of course electrons can move faster. But if you think only about lattice, then it's wave interaction with just crystal. This is why I think it's quite good to remember that. And it's just like a box, and waves are penetrating there, and they are interacting with the crystal. Then, if you believe in that, then I can ask you, what parameter really controls the result of this interaction, I mean, between wave and periodic lattice? What is the parameter that, if the parameter is bigger or smaller, then there is interaction or no interaction? What is this parameter or ratio? I suggest you build one group here. There is a group. So you build your group here, and there is another group here, if you can come here. So please discuss this question. What parameter or ratio controls, governs the result of interaction between electron wave and periodic lattice? There is really one parameter, only one, or ratio, say parameter. We have exactly discussed it already. Try to discuss in between. I know it's difficult to discuss when you are forced to discuss, but try. Try to concentrate on that question now. If you know the answer, tell me. If you don't need a discussion, it's also fine. K vector of the wave and the size of the Brillouin zone. If K vector comes to here, it will interact. If the K vector is smaller than the Brillouin size, it will, or bigger. So it's like here. So these electrons, they will never interact with the lattice. But these electrons having this energy, bigger K, bigger energy, they start to interact. Exactly because the K is big. It comes to the edge. So the answer to this question is what really controls is the relationship between magnitude of K and the size of the Brillouin zone. That's it. Very kind of interesting question indeed, in my opinion, because that's the only thing that matters. Then another question, maybe we jump over this one. Yeah. So this question we also discussed a little bit. Number 4. What is really electron mean free path? What is the diffusion path of electrons without collisions? So in free electron gas model, it is assumed, we had this drawing here. Obviously, electron is negatively charged. The atom is positively charged. So when negative charge passes by, there should be some interaction. And this is what they think in this model. And then I'm asking, is this assumption reasonable? Can you discuss in your groups that electron collide with each atom? When it is passing the atom, it collides. Is this assumption reasonable? At some point of time, it was very reasonable assumption, 100 years ago. Yeah. And I suggest you not only look into the notes, but also can talk. Because you can help each other by talking, basically. Discuss in groups. Yeah. It's somehow related to what we just discussed here. Yeah? Because electrons are not only particles, they are waves. So, okay, enough. So what do you think, guys? What was the result of your discussion? You didn't have much. But say, what do you think, personally? Don't worry, we are discussing. You don't need to get scared. So did you understand the question here? Number 4. No, now we talk about number 4. Okay, so you didn't get it. Okay, you are excused. Next time I will tell you personally what question we discussed. What do you think here, guys? The mean free path of electron, is it that small as the interatomic distance? Or is it, which is, as I said, electron is negatively charged. The atoms, they are usually positively charged in letters. They have donated the electron. So they lost negative charge, so they're positively charged. And when negative charge passes by a positive charge, there should be some electrostatic interaction. It's like now when I'm passing here, you have some tension now, you have some stress because the teacher passes by you, so we have some polarity, you know. It's the same here, correct? So it seems reasonable, but it is wrong. Because, again, because of this this consideration, which is again the key of everything. If the energy is small, if the electron energy is small, then electron just don't see the lattice. It just does not interact. It's like if you would be, you are, but if say, okay, your situation and teacher passing by, if you would know everything exactly like me, you would have no problem. I'm passing by. We are not really even interacting because we don't need to talk to each other. But this is kind of a similarity. So if electron energy is small, then it will not really get in conflict with the lattice. So when electron energy is small, K is small, energy is small, electrons don't interact with the lattice. So this is the reason for a very long diffusion length or mean free path for electrons in the lattice. Okay, next question. It's not going to be that easy. But let's choose. Let's talk about number 6. Please read it. I will read it for you too. So in this model here, exactly in this model, which is called free electron Fermi gas model, to find this, to find the dispersion, we look on the system like there is one electron, and then we calculate all orbitals. And then we populate all electrons, all 10 to 22 electrons on these orbitals. Correct? That is start of the question. And then the question is, why then, it's actually almost the answer, but anyhow, can you discuss that? Then if you do it like this, then we come up with the highest energy possible and also obviously highest K vector possible. Please discuss that in the small groups. if you understood this point. So, once again, we try to find energy of electrons. We look on one electron and we calculate all possible orbitals. And then we have many electrons, we put 2 electrons on each orbital. And then, when we exhausted these electrons, we have the highest energy. That is the meaning of Fermi energy. That is basically the answer. So in this question, there is already an answer. Yeah. But I want you to grasp this idea in a discussion. Can you please talk in between? Yeah. Yeah. Yes. Thank you very much. Thank you very much that you do it so optimistically. So indeed, just because of this methodology, that we first calculate of orbitals, all orbitals, and then we know 2 electrons on each orbital, then we have 10 to 20, I don't know, 10 to 22 electrons. We put all electrons, and then we, out of electrons, this is the highest energy. That's it. And energy is related to K. If we have the highest energy, then we have the highest K. This, okay. Very nice. Now I suggest very last question before we continue with next topic. Here, this is an interesting question. Because if I said, here we discussed, and I said it is so fundamental that if electron wave has a small k or a small energy, it will not interact with the crystal because it is not diffracted. So then, imagine if you have a low temperature, small k numbers, then probably resistivity should be 0 at all. Because all these electrons, if electrons are having small energy, they don't touch the Brillouin zone. The K vector is not really coming to the Brillouin zone H. Say it is very small. Then this vector will never interact with the lattice. But then, if this is correct, and this is correct, really, this is like that. What is the reason for resistivity then? Why there is still electrical resistance? If electrons don't interact with the lattice, what is the reason for the electrical resistance? This is a question here. I think very, very good question. What is the reason? Number 8. Oh, sorry, number 9. Please, this is relevant for us. What mechanisms are responsible for electrical resistance at low and at high temperatures? And once again, we are in terms of this model. This model tells us that we are somewhere here. So energy of electron, or K vector, is low. So electrons don't see the lattice, don't see positive charge. This is clear for us already. But then still, they don't go for, infinitive lengths. There is something that stops. And then my question is, what is that? And then there are two possibilities to consider, at low temperatures and at high temperatures. No. I'm not talking about superconductors here, not about superconductors, just normal materials, like semiconductors. Try to think about this question in the groups again. I suggest we really make a discussion now, because it's relevant for us.
You mean original lattice vibration?
Oh, no, I didn't talk about vibrations. This is a very good point. I talked only about electrostatic, about the interaction between electrons and lattice, not vibrations. Vibrations are exactly the reason. Yes, yes. Very good point. Because we have to distinguish between lattice, the planes, and vibrations. These are two different reasons. You have a very good point. Tell it to yes. Yeah? K is smaller than the size of the balloon. Yes.
아니 근데 K가 충분히 작을 때 전기저항은 무슨 의미냐, 광순의 의미냐 이 말이에요.
Yes. Because of this consideration we
전기 저항이 존재하는데 나타나는 근데 그게 뭔데 각자와의 그런 인터랙션.
it can move actually everywhere. But this idea is when electron interacts with electrons. If the magnitude of K is small, it is not interacting with electrons. This is the point. It's not really, it's not a plus, because these are reciprocal points. It's not a direct atom. These are not atoms. Because this is a reciprocal space. It's a reciprocal space. You are confused, I know. Yeah.
magnitude for this one as your
I don't know, I'm not sure I understand you, but don't think about this. Think about one-dimensional situation. Think about this. So this is K axis. So if electron has small k close to 0, just here, then it will not for one-dimensional sample, just one dimension, then these things is just these values. Because you see the smallest vibration we can have is this, and the biggest vibration is that. So this is the biggest that is possible. So when K is coming to this value, then the crystal or electrons start to interact with the crystal. Before that, it does not interact. Yeah, I can repeat. It's probably you probably need to try it on your own to try to understand, because it's really geometrical consideration. It's a consideration of Laue condition and Bragg plan that leads us to the idea of the Brillouin zone. It's simply really geometrical consideration, and it holds to all possible type of waves, to X-rays, elastic waves, and electron waves. Yeah, yes, yeah. But let us discuss this one. Because if everything that we discussed about this Brillouin zone thing is correct, why these electrons are going to, what is going to stop these electrons if they move? Because nothing can stop them. They don't interact with the lattice. But Kuocw, correct? Yes, it's easy for me. He mentioned one important thing, vibrations. Because if atoms would just stay exactly in their positions, there will be no resistivity at all, exactly as we just discussed. If atoms stay exactly in their positions, electrons would not see them. But because they move, they go out of this, simply they are phonons. So this is another type of particles. So electrons can get collide to a phonon. So this is basically the reason for resistivity at high temperatures. But then at low temperatures, why do we have a resistivity? Of course, it's actually very well known that in metals, for instance, if we talk about metals, then what is a typical plot for the resistivity? You probably know that. So if this is resistivity and this is temperature, for semiconductors it's different, but for metals it's something like this. It's not really at the very end it will probably go down, but it's basically like that. We are not talking about some microkelvin or something, but say up to, if you talk about up to 1 Kelvin, it will walk like this in normal metals. Why? Yeah, here, as Kant said, the decrease is because, or let's say, with temperature, the increase in resistivity is simply because there is electron and there is a phonon. Let me put it like this, phonon. So when electron comes here, it collides with the vibration. But the magnitude of this decreases with temperature. So at some point, it actually should go to 0. But it doesn't. And the only reason for that is what? Yes? Between electrons themselves. No, it's not possible because electrons are fermions. They actually don't interact. They want to go out, away from each other, really. They don't really like. They have to be on their own quantum number. They cannot really get. But the reason for that are either impurities, but even you have a very pure material, is the defects. Because even at very low temperature, you always have some imperfections in the crystal, vacancies, things like that. So that is the reason. Yeah, by the way, let us jump a little bit ahead. What is the temperature dependence? What is the resistivity dependence? Or let's say maybe not resistivity, say conductivity dependence is better for a semiconductor. How does it look like? That you should know.
It decreases as temperature goes up.
So do you like me to put it 1 over T maybe is better? Yeah, okay. How does it look like? You can talk about that in the groups. Yeah? Did you understand the question? Good. So this is metal. This is semiconductor. So this is high part, this is low temperature part. So what do you think how it should go?
Similar shape.
Similar?
Upward direction. Yes.
But let me put it like this. So is the conductivity low or higher at low temperatures?
Low temperature.
Low this is
Yeah,
this
low.
1 over T. Should I have a point here or should I have a point there? This is conductivity.
Conductivity. Low conductivity.
Good. We start from here.
Yes.
Okay. At this situation, should I come to low conductivity or high conductivity? Good. We have 2 points. Now we just have to connect these two. How should I connect? Should I connect like this or how should I connect? Yeah, good point. But for anything, or if I do like this, is it correct? Maybe I can even draw it. I can put even a logarithm here, and then I put a straight line. This is correct. No? You want to have it like this? Oh, sorry, it's not should be like that. Yeah. I would say that both are correct. And this would be so-called, maybe this is not really perfectly correct. The correct would be this one. Yeah. And this would be related to so-called intrinsic. And this would be related to doped material, correct? Yeah. So because even in the doped material, these parts are identical, because when temperature goes high, we will talk very much in details about that next time. But you see how different it is. So it's actually totally different, because if we try to make it in the same coordinates, if you try to draw conductivity, and if you put 1 over T here, so then for metal, so this is low temperature. So low temperature we come to some point, also low. But at high temperature, conductivity is also low because of vibrations. So in metal is actually a little bit complicated. It may be quite complicated. Depends on the temperature part and also here. So what would be even better is to consider also electron concentration. And for instance, for metal, what would be electron concentration for metal as a function of temperature? Actually, it is very simple. It's constant. But in this material, it is exactly like that. Yeah. So very good. So you know that. I'm very happy. So let us continue working with one very important part. And this part will introduce the idea of holes. Maybe I will just jump. Over one topic, because it's already, we talked origin of the band gap. We talked about that. Actually, the origin of the band gaps is exactly because of this. So wave interact with the lattice, and exactly at these points, at these positions, we have a diffraction, and that results in the change of energy. But probably we should. It's a bit complicated. It's a bit complicated consideration, but maybe we should take it. I have this slide. Maybe I should. It's a bit complicated slide, but let me try to guide you through this slide. This is the simplest possible explanation for idea of the band gaps. Yeah, I go to the next one. Yeah. It's not that complex. Maybe in some courses, in some, I'm sorry, I want to jump back basically to this one. I'm sorry for that, jumping back and forth, but I'm just jumping here. Yeah. So in very, very introductory courses, what you've been told, I think, is like that. Again, there is an atom, for instance, sodium. And on sodium atom, there could be one electron. Could be one electron, exactly this one. This is a sodium atom. Of course, the atom is bigger, but it's just the last electron. The last electron on the most outer shell. This is one sodium atom. And this is another sodium atom. And these two electrons, of course, when sodium atoms are far away from each other, they have exactly identical. It's like a watch. Exactly 1 second here, exactly 1 second there. They're just identical. When you move these two atoms, two systems closer to each other, what happens is that this electron cannot be identical any longer, exactly because of this principle, of this Pauli principle. We cannot have too many identical electrons, actually only two on one energy state with two different spins. Because of that, this energy level is not applicable, is not good. It's like, I don't know, like people. When you go somewhere, you adapt. For instance, you go to Europe. Now you are very far from Europe. You really don't care. I don't know, Europe, or I don't know, China, different place. And then you have to get adapted. So you change a little bit. You are still you, but you can get adapted. Basically something like that. So they get closer to each other. They have no way. They have to get adapted. And this energy that was the same initially for two different electrons, it really split a little bit. Just in order not to keep the same position. It's not good. And when you have two electrons, you have only two positions that get split. But when you have 10 to 25, or sorry, 10 to 22, like in silicon, for instance, instead of these two discrete levels, of course, what you get, you get, these are two discrete levels, and when you have so many, then you get a quasi-continuous band. This basically is the reason for, I would say that this explanation is probably the simplest, but it is very qualitative. So the reason for appearing of energy bands in these terms is actually Pauli exclusion principle. If there would be no Pauli exclusion principle, then all electrons could be with the same energy. There would be never bands. If you don't need to adapt, we would be ourselves all the way. But somehow we adapted to society, to our parents, to whatever. So it's getting more complicated. That is probably the easiest explanation, but it is very qualitative explanation. But the next easy explanation is the following. I'm going to show you that. So now we have these functions that we talked already about many times. This is our electron, and it goes through the crystal. This is our electron, and it goes through the crystal. So if this value is small, you just don't see the crystal, as we also discussed. We talked long about that, yeah. Because the vector, k vector, is smaller than the size of the Brillouin zone. But then, if k vector comes to the conditions that diffraction happens, then we have this situation. So for these values, for for, sorry, not here, I think next, yeah, for these values. So this is D. So when K is exactly equal as we have it on the reciprocal space, on the Brillouin zone size. So this is exactly where the diffraction happens. And then we just can have it at that plane, at this plane, at any plane of that kind. So this is why we have this n. But you can just disregard that. K is equal 1 over D. When K is equal 1 over D, and K is just distance between planes, then there is diffraction. That's how it is. It's a phenomenon. And then I can calculate, I can just plug these values of K. And next slide is going to be very complicated. You see. But what is done in the next slide? I just take these values of K and put it in there. Because I know that diffraction happens in this case. So I just take it in there and write out. Because this is also equal to sine, a combination of sine and cosine. Let us see. So you see what is here. Here, I take this value of K and put it inside this exponential equation. And this exponential equation, then, and you see it's plus and minus, I just write it. I just write it in. It's a bit complicated, but if you look, you took this K, put it in here. You've got plus or minus, and then you can have two different combinations. You can either, these are all good solutions. So this is a good wave function. This is a good K. And then because you have plus and minus, you can have two combinations, just mathematically. Either this one or this one. So you can plus them or we can subtract them. It's a little bit, I know it's a little bit, how should I say, theoretical now. But you can do that. I know. I did it once. And I know it is true. So we know that in this case, there is diffraction. We plug this into here. Make two possible solutions. And then remember that exponent can be developed in a combination of sines and cosines. Because of this plus sign, you're going to get cos here. Because of this minus sign, you're going to get sine here. That's it. That's how it is. You should do it. But if you believe that you have two different solutions for these values of K, I can just plot these two different solutions on the next slide. So what is done here is really interesting. And I suggest you a little bit concentrate now. So what is done here? You see, this is sine function. Sine function is this one, correct? This is sine. This is low, at low magnitude at low argument. This is sine. This one. And this one here is cosine. And what is here is, say this is my 0 point. This is my atom, and this is my atom now. This is another atom. This is another atom. Another atom, another atom. This is a potential that is created by these atoms. And these two functions, sine and cosine solutions for the electron wave for exactly this K point. And now is going to be a huge progress, a huge trick that you are going to experience. What does mean this is an atom? It means that there is a positive charge here. Because the atom, say it was sodium. Sodium has donated its electron, the rest of sodium is positively charged. So here we have a positive charge. what is this? Yes, this is electron wave. Basically, electron. It tells us where the electron is going to be. So when the magnitude of this is big, then the probability of electron to be here, for instance, is big. For this solution, for this one, the highest probability for electron to be is here. For this solution, the highest probability for electron to be is here, for cosine. Just that's how math works. And then now is coming the trick. So electron is minus sign. This is plus sign. If my electron is mainly distributed here, then this is my sort of distance between one charge or another charge. And you know that the energy for interaction, electrostatic energy, is inversely proportional to the distance, correct? You remember that? Energy for electrostatic interaction is inversely proportional to the distance. Then, here I have this big distance between charges. Here I have no distance actually, very small distance. So it means that for this electron, I will have huge interaction. But for this electron, I will have small interaction because they're simply positioned at two different. It's like, let me draw it again. It's like I have positive charge here, and then most likely I have negative charge there or here. Obviously, I mean, I should probably draw it like that. So this distance is short, this distance is long. This is what you see here in between this point, and this point, and this point. There are two possibilities for interaction between the charges. It means that this interaction will provide big energy, and this interaction will provide small energy. Or at least, let's say, this is going to be bigger and this is going to be smaller. And that is why now we can come to this picture of the band gap. I think you are going to sort of, I hope you are going to experience a discovery now. So remember, this was our curve, our dispersion curve. Energy is equal to this, k squared. And then in k, in points, this is k, this is energy. In the points pi over d, this is exactly point that we talk about. So here we have diffraction. And because of this situation that we have two different distances between charges, so instead having one energy point here, we got actually two energy points, exactly for the same k. One is low and other is big. Exactly what I draw here. This is really important. Maybe you never heard it before, because usually this part is neglected, but this is really the simplest explanation, more or less qualitative, but still have some theory behind. Why do we have this split in energy? Because the only reason for this split in energy is that, once again, we have diffraction. Our k is of that order, pi over d. We can go to this famous, now famous, I hope. let me jump long back. Here. So, this is k, So when k comes to this point, we have diffraction. As long as k is smaller or bigger, we have no really interaction between wave and the crystal. This was good, but how do we know that we have this, and how big is the split in the band gap? Now we know. Now we know, because the split in the band gap is exactly because of this phenomenon here that is illustrated by this cartoon here. That exactly in these k numbers, we have two solutions for the wave function. One is cos-like, and the other is sine-like. So that the distance between the lattice and the electron in one case is short, in other case is long, which give us one energy and another energy. So this part is totally disappearing. You see? This is fantastic. Because really, to get it really strict and correct, you need a very complex mass. And as I like, is to avoid this mess, but to get understanding. Because all the mess that you do, it doesn't bring more understanding than we did it now. This is a true reason for having a band gap. One is basically that we have periodic structure and we have electrostatic interaction. There are two components. And by considering the electrostatic interaction here, we can say that we have a split and how big the split is. That's it. I don't know if you ever heard about that before, but I have my own experience, not so good, that in lectures, there are either very simple lectures, that trivial, or very complex lectures that are impossible to understand. So what I try to do is to find something in between, that we get essence of physics, but try to avoid complicated math. That is really impossible to do on a lecture. Right. Yeah, I suggest we stop here and continue. So now we are done with theory. So 2 last lectures are going to be about semiconductors. Going to be a lot of fun. Yeah, thank you very much.